Hi everyone, what's up? Today I want to show you how to find a tangent plane in 3 space by solving this example, okay? So this is a very simple example. We need to find the equation of the plane that is tangent to the surface x times y squared at this point, 1, 2, okay? This is a very simple problem, and the strategy that I will use for this problem can be applied to a whole bunch of problems, okay? So I'm just gonna get right into it. So if you want to find a tangent plane, I think the easiest thing to do, if you're given a function and you can take the derivative of this function, sometimes you may not be able to find a derivative, but in most cases you will be able to. So if you have a function, you can use the approximation formula in the multivariable approximation formula to find the equation of a plane, okay? So hopefully you can recall back from single variable calculus, there was a formula in which you could find a way to linearize functions, meaning if you had a curve, you could find a line that is tangent to that curve, and then the function will be close to that line if you evaluate the function at points close to the point where the line is tangent to, okay, or tangent at. So there's a very similar idea here, and the formula that I will use goes like this. The change, or any change in our variable c, will be approximately the same as the partial derivative of c with respect to x evaluated at our point x naught, y naught, and then you're going to multiply this derivative by delta x, okay? And then, since we have two variables, we're going to do something very similar. We're going to have partial c, partial y, and we're going to evaluate the derivative at x naught, y naught, and then we're going to multiply by delta y, okay? Now this formula is the same thing. I won't use partial notation anymore. Hopefully you know that another way to write partial derivatives is like this. You can say, and actually, yeah, I'm going to say f, because I think it's the most common notation. And so I'm going to say something here. F is going to be equal to c, which is going to be equal to xy squared, and you're going to see why I'm doing this. I just want to be clear about notation. Instead of writing partials, I'm going to write this using this notation, f sub x, and we know f equals c, that's why I had to indicate this. So this can also be written as the derivatives evaluated at this point times, and actually I want to, instead of using delta notation, I will use this notation, x minus x naught plus the derivative with respect to y evaluated at our point of interest times y minus y naught, okay? So hopefully you can see what I just wrote from there. Over here we have the derivatives. This is going to be the derivative partial c partial x evaluated at a point times a change in x, that is x minus x naught, plus f sub y evaluated at the point we're interested in, and then times the change in y, okay? Now notice here I use the equal sign because these two expressions are equal to each other, but they're approximately the same as delta c, okay? So also, yeah, over here you can see the difference. So now the only thing that we need to do here is that, well, hopefully you know about a form for planes, for equations of planes, that is the point normal form. So really, if you want to find the equation of a plane, there is a shape that you can follow, and it's this one. 0 is going to be equal to a times x minus x naught plus b times y minus y naught plus c times c minus c naught. Now this is the equation of a plane pretty much, and this plane will have a normal vector with components a, b, and c, and it's going to contain the point x naught, y naught, and c naught, okay? Now hopefully I want to emphasize the resemblance between this equation, which hopefully you're familiar with. If you're not familiar with this equation, just be confident that this is the equation for a plane. You have a normal vector, meaning a vector that's perpendicular to a plane with components a, b, and c, and then the naught points, the x naught, y naught, and c naught, they're going to be it's just going to be they're just going to be, these numbers, they will be the coordinates for a point in the plane. Now hopefully you see some resemblance between this expression and this. So something we can do, and also you have c minus c naught, and over here you have delta c. That's pretty similar. Hopefully you see where I'm trying to go here. Something you can do is, instead of using this equation, which for now we may be able to use this equation. It's going to be easier to use this, okay, because we have the derivatives. We have f sub y and f sub x. We just need to compute them, but we can do it because we've got the expression up here. And over here, if we didn't have the function itself, if we didn't know what c is equal to in terms of x and y, then it may be kind of hard, and maybe we would have to figure out how to find a, b, and c. There may be some way, yes, but for now, I will not use this equation. I just wanted to address why you would not use this equation in this problem. Or, if you're just given the function, you might as well just take its derivatives, because it's going to be easier than finding a normal vector, okay? So now let's go with the derivatives. So what we're going to do is the following. First of all, we're going to find the derivatives. So this is going to be partial c, partial x. Now what is that going to be equal to? So we're going to have, if we differentiate with respect to x, well, that's just going to be y squared. Now let's do partial c with respect to y. And we know that this is going to be 2xy, okay? Now, using this expression, we have the following. A change in c, so c minus c naught, is going to be equal to, so now the derivative with respect to x evaluated at x naught and y naught, well, what is that going to be? Well, x naught equals 1, so we're going to have the derivative with respect to x evaluated at x naught equals 1 and y naught equals 2, we only have y, so this will be 2 squared, meaning 4 times the change in x, so this is going to be x minus, and now minus what? Well, x naught, again, it's going to be 1, so minus 1. And we do the same thing for f sub y, so we have 2xy as the derivative with respect to y, and we plug in these values, so we're going to have, this is just the same as 4, again, so this will be plus 4 times y minus y naught, that's going to be 2, okay? And now, you may be wondering, well, what about c naught? Well, remember, hopefully you remember back from, a couple of, maybe you solved a couple of single variable calculus problems in which you're only given an input, a point, and then you had to find an output at that point. Here, I deliberately didn't give you what c naught was equal to, but I did give you the point of interest, or the input of interest, which is just going to be y naught and x naught and y naught, 1, 2, okay? So what am I trying to say? Well, I just want to say that c is going to be equal to c naught is going to be equal to these points evaluated or, inputted into the function, okay? So if you want to find c naught, well, really, you just have to find the function evaluated at these points. Hopefully, it's pretty intuitive. But some students, they have trouble visualizing, well, what is c naught going to be equal to? It's the same thing as doing single variable calculus. You may be given an x naught point, and you need to find a y naught point. Well, then just evaluate your y function at x naught, okay? Same thing here. So now c naught, well, what is that going to be equal to? So we're going to have, I'm going to do it down here. So we're going to have c minus, and now let's evaluate this here. So this will be 1 times 2 squared, again, 4. So this will be minus 4 is going to be equal to 4x minus 4 plus 4y minus, so 4y minus 8, okay? Now let's move all the constants to the left and all the variables to the right side. So we're going to have, this will be, can we divide? No, we can't factor everything. I was going to divide by 4, but we can't. I mean, we would get a coefficient that is not an integer for c, and I just want to have integers, okay? So we're just going to have here that the equation of the plane is going to be 4x plus 4y, and then we're going to have minus c, or z, I prefer to pronounce this as c. And then we know this will be equal to, so we have, we move this a to the other side, this is really going to be minus 12 plus 12, that will be 8 on the other side. That's kind of ugly. 8, yeah, that looks better. So yep, this is what we get. This is going to be the equation of the plane. And now there is a very nice, so this is going to be the equation of the plane that is tangent to this surface at this particular point, okay? This is the equation. Now there is something you can do here in, using the same reasoning that you used to say that a function is approximately equal to its tangent line at a particular point. Well, we can also say that a surface, which is going to have for output c, is going to be very similar or very close approximately to its plane tangent at that point. So I want to say the following. Even though here we're using equal notation, you can also say that C is going to be approximately the same as, and now you just simply write everything out, the equation of the plane pretty much. So 4x plus 4y, and if we move this 4 to the other side, we're going to have minus 8. So this is another way in which you can linearize, that's what we call, because we're just using linear terms. Not really, because this is a linear function. It's a composition of linear functions. So you get a plane because you're in space. But yeah, we just say that this is the linearization of C because you're just using linear terms. And this is another way in which you can say that, well, this is approximately the same as x y squared. So this is a way in which you can approximate functions. Say that if this function was way more complicated, and for some strange reason, maybe it's easier to linearize the function, well, then you can do this, and then this will be true. So this approximation will be true for values. So for x, y's near 1, 2. Okay, that was the point we were given. So this is how you can also, you can use a plane to approximate a multivariable function. And yeah, this would be the reasoning behind doing that, okay? So yeah, this has been the entire video. Hopefully you enjoyed it. It's a pretty simple problem as long as you know this equation, this approximation formula. This is really helpful in multivariable calculus. You're gonna see this formula a lot. You can get a lot of concepts and ideas from this. So yeah, you should really know this. And yeah, that's been the entire video. Hopefully you enjoyed it, and see you in the following one. Bye.